Welcome to Chapter 3, Point Groups. Point groups use symmetry to classify the shapes of individual objects. The object can be a molecule, such as pentacene, or it could be a chair, or it could be a painting, or it could be a scene outside, or it could be any number of things. We will usually concentrate mostly on molecules. The main part of this chapter is on section 2.3 is group theory. Before we start group theory in section 3.2.1, we will discuss first of all a set and the elements in a set. A set is a collection of elements. The elements could be A, B, and D, and the set is the combination of A, B, and D, and when we list the elements of a set, we put these curly brackets around it. It could also be a top, a box, and a hat, and we could have that as our set. It's a very wide concept. We can also indicate sets by a description. Sets can be integers, for example, greater than 3. Or another example is the set could be 4, 5, 6, 7, 8, all the way up as far as you can go, and that set is infinite. That is, the sets can be infinite or they can be finite. An element can also be an operation, such as a rotation. 3 plus is a counterclockwise rotation. It goes around like this, counterclockwise, and a rotation of 120 degrees, so that's about to there. And we would indicate this set, which consisted of this one rotation, as 3 plus within the curly brackets. We can have a set of 3 numbers, 0, 1, and 2, and we can model this set in terms of an alarm clock. Our clocks are usually from 1 to 12, or if you have a military clock, from 1 to 24, but let's consider our clock to be 0, 1, 2, 0, 1, 2, going round and round. Next we'll consider operations. The operation of a group is indicated by the symbol, a little plus sign with a circle around it, red operation. For example, a group could consist of the set of 1, 2, and 3, and the operation of addition mod 3. Let's examine that a little more. Here's our circle with 0, 1, 2, and here's our elements. We put our elements in a row, and we repeat the elements again in a row, and we have the operation in this corner up here. So 0, operation 0, is represented in this box, so 0, add 0 to that, and we get 0. All of the operations are indicated, for example, 1, operation 1, so 1, operation 1 would be, now add 1 to it, and we get up to 2. So 1, operation 1 is equal to 2, and if we have 1, operation 2, so 1, operation 1, 2, that's going to equal 0. So 1, operation 2 is going to equal 0. We don't need to write out the details in each of the boxes, so here's what we call our multiplication table, or our Cayley table. We put the operation in the corner, the elements across the row and the column, and then the products, or the elements times the operation, and it's often referred to as a column because the whole table is called a multiplication table, but it's meant in the abstract sense of multiplication. So for a finite group, the multiplication gives all the possible combinations relating two elements by the operation of the group. So you take any two elements, 0, and 1. So we relate 0 operation 1 and we get 0 operation 1 and we get 1. So this is a way of displaying the relationship between the various elements. The order or sequence of the elements is important for many groups. That is, sometimes the element times the element operation element is element 1 operation element 2 is different from element 2 operation element 1. But in this case, that's not the case, and you can tell that by the Cayley table or the multiplication table, because the off-diagonal terms, namely the 1s, the 2s, and the 0s in this case, are all identical. If they're identical, then you have what we call a commuting table, but they don't have to be. And we'll have examples of those. Now we're going to put all that together and get a group. Here's a group of giraffes. That's another kind of group, but we're dealing with abstract mathematical groups. So we have our elements, 0, 1, and 2, and our operation, addition, mod 3. And the next thing we have to have is 4 properties, the first of which is closure. So the closure means that for any operation between any 2 elements, A and B, then A operation B is equal to C, where C is also in G. So what that means is, in this case we have 0, 1, 2, here we have 0, 1, 2, and if you look at the next 2 lines, they're simply permutations of 0, 1, 2. Again, we don't have any repeats, but we do have permutations. Again, if you look at the columns, here we have 0, 1, 2. Again, we have 1, 2, 0, and here we have 2, 0, 0, which gives us also permutations of 0, 1, and 2. On the other hand, if we had 1 operation 1, and that in some system might equal 3, 3 would not be in here, so you would not have closure. It's a very useful concept, which we'll see a little bit later. Next, we need to have, to have a group, we need to have an identity. So an identity is the element in G, such as the identity operation A is equal to A operation identity is equal to the original element. So in this case, you can see that 0 times 0, 1, 2 gives you 0, 1, 2. So if this is E times each of the elements is going to give those elements back. And on the other hand, to get the multiplication going the other way, we can have 0, 1, 2 times each one individually times 0, and we again do 0, 1, 2. So we can see from that the identity here is equal to 0. And now we need to look at the inverse. So once we have an identity, for every element in the set, we have to have an inverse such that A operation A inverse is equal to A inverse operation A, which is equal to the identity. For example, 0 times what is 0? Well, 0 times 0 is 0. So the inverse of 0 is 0 because 0 operation 0 gives it back itself. 1 is the inverse of 2, since 2 times what is going to give me 0. Well, 2 times what is, here's my 0, so it's 2 times 1 equals 0. So 1 is the inverse of 2, because 2 times 1 equals 1. 1 times 2 is also equal to 0. So we have 2 having as its inverse 1. Now you tell me what the inverse of 1 is. Well, I think you got it right. 2 is the inverse of 1, since 1 operation 2, so it's 1 operation 2 is equal to the identity, and 2 operation 1 is also equal to the identity. So you have the inverse of each of the elements exhibited. And finally, we have the associative law, and that tells us that given A and B, and the parentheses tell you to do this operation first, followed by C, you can change the parentheses so you could do the B operation C, and that could be multiplied A times that. Notice I use the multiplication time, the asterisk, which is the ordinary computer symbol for multiplication, which is generally what you're referring to. So people will use that. You'll see that in the literature. But it's an abstract thought of multiplication. So let's exhibit that for one case. So we're looking at 1 operation 2. So 1 operation 2 is going to give me 0. So this is going to give me 0. And then 0 operation 1 will give me 0. Operation 1 will give me 1. Now we'll put the parenthesis around the second 2 numbers. So we'll have 1 multiplied by open parenthesis 2 operation 1 close parenthesis, which you can see is right here. And if you work that out the way I did it above, you'll get 1 back again. So now we've demonstrated, we haven't actually proved it, because to prove it we'd have to go through all of the examples. And now let's just summarize. We have, to have a group, we're going to have elements, and here are our elements. In this particular case, we're going to have an operation. We're going to have closure, which means no more new elements. We'll have an identity, which in this case is 0. We'll have an inverse, which we've demonstrated, and we've shown that, or demonstrated that the associative law at least holds, and if you went through the rest of the examples in the book, you would see that they, in the multiplication table, you would see that they work too. So that our definition of a group is a set of elements with an operation between pairs of elements that has the following 4 properties: closure, identity, inverse element, and associative law. I expect you to know that as a definition. The elements of the group can be operations. For example, E could be the arrow just standing still. 3 plus is a counterclockwise rotation of 120 degrees, so the arrow comes down here. And 3 minus is counterclockwise 120, counterclockwise another 120, and that brings you back over here to 3 minus. So here's our group, E, 3 plus and 3 minus. Here's our multiplication table, and the operation here is rotation. And the elements are elements of our operations themselves. We can define a group by a multiplication table, so that's all we have to give is the multiplication table, but the multiplication table has to, in addition, demonstrate the four necessary properties of closure, identity, inverse, and associative law. So now let's go on and look at individual symmetry operations. Here's a nice little family of 3 giraffes who's coming to say hello. Symmetry operation can be demonstrated by looking at this triangle, and now suppose we rotate the triangle around its center axis, which is right in the middle here, and if we rotate it by minus 120 degrees, we simply get the same triangle back. We could not distinguish between, if you closed your eyes between the operation, you couldn't really distinguish. Now, if somebody knows how to demonstrate or give the motion of the 120 degrees, I'd be very grateful for that, and I'd be happy to give that as extra credit, and a lot of extra credit, like a quiz. Okay, here's an example of something that is not a symmetry operation. Consider the square. Now, if this object is subjected to a 3 plus, it comes out to looking something like this when it's rotated by 120 degrees counterclockwise. And so you certainly can tell the difference. You can tell something has happened to the object under the operation. So this is not a symmetry operation of the figure. So here's our definition of symmetry operation. You know how important I like definitions. A symmetry operation is an operation in which the object looks the same before and after the operation. Now let's look at a convention that we're going to need for the international tables for crystallography. We will be using that in chapter 4 and for the rest of the book afterwards, but we're getting ready for the tables. And the convention for the tables is, if you start up here in the upper left-hand corner with the origin, and if you extend a horizontal line going from left to right, that becomes the y-axis, which is the positive y-axis, goes from left to right. The x-axis points downward, so that if you had the x and y-axis were 90 degrees apart, then the x-axis would come down like that. In general, they'll be gamma number of degrees apart. So here is the angle gamma, and here is the x-axis appropriate to that gamma angle. Notice here is the point xy. This is the positive quadrant here. The negative quadrant is up there. And along here we have the projection onto the x-axis, and along here we have the projection to the y-axis. So that's x, y. And it's always done in the order of x, y, just like it is for your previous life. We're going to look at this wonderful mirror symmetry operation, and who recognizes this? Well, it's Pandapa's Pond here close to Virginia Tech, and I hope you all go and visit it at least a bit before you graduate. There's a wonderful walk around the two lakes, and then there's wonderful walks up into the mountains, which we enjoy very much. Here you have the setting sun, and it's just coming down below the horizon, and you can see it reflected here. And here's a tree reflected down here, and that tree is up there. And this is a tuft of grass that we're looking at directly, so we don't have a projection on that. And you can even see this little cloud here is all the way up there, and these little clouds are up on the top as well. Here's another example of a mirror plane. This was taken on our trip to the the International Crystallographic Association in Japan, and this is the Golden Pavilion. And you can see the mirror plane here and the Golden Pavilion being reflected upside down. The mirror symmetry operations, we need to calibrate them and to actually label them and to give analytical expressions for them. So here we start with the what we'll call later the asymmetric unit, and then we'll put the operation of the mirror, and then when we put the mirror, the horizontal mirror, we're going to get the whole figure of the B. We indicate the mirror by this purple line. So the definition of a mirror is a symmetry operation of reflection. The symmetry operation for a mirror plane is a heavy solid line, and the mirror plane in purple is described as M at 0y. So that means that the x component is going to be always 0, and the y component can be anything at all. It can be any It can be positive or negative. We're not restricting it. So here's the description. And now we wish to look and get some more analytical expressions. We have this mirror plane. We're going to subscript this as m sub y at 0, y, which we've just described. And now we will take a point. So here is the point 1, 0, a unit length along the x-axis. And if we operate with the mirror plane on it, we're going to come up here to a point minus 1, 0. Remember, the positive x-axis points downward, so pointing upward would be the negative axis. So we have 0, 1, 0 going into 1 bar 0. And in general, if you have some point x, that point will be reflected up here into minus x. So we, in effect, are multiplying across by x, so it's x times 0 is equal to, or rather, x comma 0 is equal to x bar comma 0. Now, what happens to y when we undergo the mirror plane? Where does y go? You tell me that. Well, I hope you got it right, because y just goes into itself, because the 0, 1 point is just sitting right on the mirror plane. So let's look at that. And so we can just write 0y goes into 0y. And if we want to get the general expression, we simply combine these two general expressions along the x and y axes, and we get xy goes to x bar y. And here is the analytical expression, which shows xy going into x bar y, and then you see it being reflected across this mirror plane. We also want to associate a matrix m sub y with an operation, so every operation is going to have an associated matrix. And here we're going to operate the matrix on xy. We want to get as an answer x bar y bar. So what's the matrix that will do that? Well, if we want to turn the x into minus x, we put 1 bar 0. So let's look at that. And you can see also you get 0, 1 takes y when you multiply. 0 times x is 0, 1 times y is y, so that gives you the y. So that gives me that operation. We'll also be interested in the determinant of the matrix. And if we look at the determinant of this matrix, what is it? Well, I think you got it. It's equal to 1 bar times 1, which is minus 1, and then these cancel, so the determinant is equal to minus 1. Now let's look at a very lovely figure. This is the parametric butterfly, and you can see that along the x-axis, which is now the vertical axis, we have a mirror plane going right through our butterfly, and this is going to form a homework problem for you. It's problem 3.6, and you will be generating this wonderful butterfly. We call it the parametric butterfly. I'm going to give you a hint as to how it works. Well, it's going to be across the mx axis, so we can indicate that as a mirror, where x can be anything at all. Here's the x, but y stays the same. You have to get used to these axes. Here's a parametric equation which is graphed just like that. First we need a range. So here t is going to go from 0 to 1. So it goes from 0 to 1. And then we're going to break this axis up into many little points, and they're only 0.01 increments. And so the equation is calculated at each point here, and if we put them close together, it looks like a continuous line. It's not. These are points, and you can calculate them in terms of the parameter and then give it a plot. So here's my plot of xy. Just produces that. So this little program will produce this figure. Now, when you do the butterfly, notice that the parameter is a theta, and theta of course is an angle, so you want to have the units there going from 0 to 360, or 2 times 360, or 3 times 360, and you'll have the parameter will be, of course, theta, and I think you'll do very well in that. Now let's go and look at the identity, the symmetry operation for the identity. The symmetry operation is represented by the number 1, and it takes the point with coordinates xy into itself, or xy. The associated matrix is what? Yes, you got it. It's the identity matrix, because 1 operating on xy, or the identity, and you multiply it out, operating on xy, gives me back our very own xy. And what's the determinant? You're right, it's 1 times 1 is 1, and then the zeros cancel. Okay, now we can have any number of rotation symmetry operations. So let's look at a twofold. We're going to do 2 examples, the twofold and the threefold. The twofold, we start, perhaps we could have our figure be the S, and this little oval squinched down circle is going to be the symbol for the rotation, and we operate the rotation on the S, and we get the full S. So the definition of our twofold rotation is a 180-degree rotation that is a symmetry operation. And you can see if you take the S, you put your finger on it and you twirl the page around, you're going to not be able to distinguish between before and after twirling your page of 180 degrees. The symbol for the twofold axis is a oval that's kind of pointed at each end, but it's really easier to draw it in our various drawing programs by a circle. So an oval. So I just do that. So now we're going to look at our twofold. We indicate the twofold by a letter 2, and then we have to put our origin where the origin is. So here is the origin is going to be at 0, 0. So here's my origin. Here's the symbol for the twofold, and here's my axes. Notice they don't have to be they don't have to be perpendicular. They can be at any angle whatsoever, and you can do the operation of the twofold. And we're going to have the 1, 0 will under the twofold come up here and go 1 bar 0. What happens to the 0, 1? Well, you tell me. That's right, you come back here under the twofold, and that's 0, 1 bar. So in general, we can have 1x goes to 1 bar x, or x0 goes to x bar 0. Similarly, for 0, 1 goes to 0, 1 bar, and in general 0y goes to 0y bar, and we combine them, xy goes to x bar y bar. And we can see here, here's our xy, here's our axes, and when we do the twofold, we come over here to x bar y bar. Now what kind of a matrix will we have? Well, we just put the operation 2, and then operating on xy. What do we need to operate on xy to get x bar y bar? You tell me. Write it out. Yes, it's 1 bar 0, 0, 1 bar. You'll be required to do this in quizzes, so I expect you to be able to do it. And again, the determinant of 2 is 1. So here's the determinant. Here's my matrix, which is equal to the twofold. And 1 bar times 1 bar is +1, and the determinant is +1. Now we'll also do the threefold. We have this figure exhibits a threefold symmetry, because if you rotate it at 120 degrees, you're not going to be able to tell the figure before and after. So Definition: threefold rotation is a 120-degree rotation that is a symmetry operation. The symbol for the threefold rotation is a triangle. Notice the point is up. And now we're going to get the analytical expression. First thing we have to do, though, is see when we have a threefold here, you have the one axis and you're going to operate it on it by a threefold. You really need three axes to talk about this, and we're going to see how this happens a little bit later. This is a very interesting situation. So we could make another axis, which would be, this would be xy, and this axis here would be represented by x bar, y bar, or specifically the point 1 bar, 1 bar is right along here. So what happens to 0, 1 when we have a counterclockwise rotation of 120 degrees? 1, 0 goes into what? Yes, that's right, 0, 1. So, and in general, if you put x over here, any position, say x right there, it's going to go, when you rotate it around, it's going to go in that same position here. So this length here is preserved. So we have x0 goes to 0x. And now you look at the y. When you rotate the y through a counterclockwise rotation of 120 degrees, we come out here. So 0, 1 goes into 1 bar, 1 bar, and in general 0y goes into y bar, y bar. So now you tell me what xy goes into. Well, I hope you got this one right. xy goes into y bar, comma, x plus y bar. Well, it's a little more complicated situation, but this way of finding it out is really very nice, and you won't make a mistake if you follow this path. And you can see here, if you have position xy and you do a counterclockwise rotation of 120 degrees, you're going to get y bar x plus y bar. And now we want the matrix for 3 plus, and I think you can give me the matrix now that you've been doing that. So what is it? Write it out. Stop the tape and write it out. You need to do this. So here we go. We have 0, 1 bar, 1, 1 bar, and if you multiply that out, you'll see that you get exactly what you were expected. And the determinant of this becomes what? Well, the determinant is 1, and you can see that by multiplying that the determinant out. Now we can have lots and lots of n-folds. I'm not going to do any more of them, but on the left we have a 9-fold, and the rotation angle would be 360 divided by 9, and the figure on the right has a 30-fold, and it you can get that rotation angle by dividing 360 by 30. Now, what we're going to do, this one of the last things we'll do right now, will be the crystallographic rotations. Now, it turns out that the periodicity of the lattice limits the number of compatible rotation operations. This is absolutely an extraordinary theorem that we're going to prove, because we're going to prove that something can't exist, and that's usually pretty hard in mathematics, but I think you'll see our proof is really rather nice. And it's also independent of dimensions. I'm not going to mention anything about dimensions, so it would apply to one-dimensional, two-dimensional, three-dimensionals, which of course are those of crystallographic interest, and for theoretical reasons you may want to do any number of dimensions, and in groups this is exactly what you're going to find. The implications of this is that you're going to see some very far-reaching implications. Let's look at this pattern and this would be a pattern which we see that we can find a 4-fold in there. In fact, We have a lattice point here, and the lattice point that contains the fourfold is here. Think of this pattern as going on and on for infinity. Any fourfold will, as we rotate through 90 degrees, will get us back to the same pattern. In general, the rotation angle for an n-fold rotation is 360 divided by n. Now what we're trying to prove here is we're trying to see, is there any limitation on the number of symmetry rotations that are allowed under the condition of periodicity, because that's what we have in crystals. So now let's first prove ourselves a little lemma, or demonstrate for ourselves a little lemma. If we have vector A, which connects two lattice points, and vector B, which connects two lattice points, we can move them together so that they line up like this, and now we can add A plus B, and when we do that we get C, and the lemma says that if A and B connect lattice points, then C also connects lattice points, and I think you can see that that's exactly the case. So now, here is what we're going to start out with. We're going to start out with a lattice that contains an n-fold rotation axis, where n is an integer. So the only limitation we have on here is that n must be an integer, and that we are talking about lattices, that is, these repeats. So let's make ourselves a little vector here. So we'll connect any two lattice points A to any two lattice points to produce the lattice vector A. Now, since we don't want to prejudice ourselves, let's just get rid of the rest of the lattice and just consider this vector A, where it has an n-fold rotation axis, say around here, every lattice point, but specifically around this one, and see where we can go when we start examining that. So let's take our vector A and rotate it clockwise through the angle of the rotation that we're testing, and we come out with A prime, and that connects these two lattice points. They have to be lattice points because the rotation axis will operate on our original axis. We can go a rotation counterclockwise by theta, and we come up to A double prime, and if we break up A prime and A double prime, we see that they both have components along the vertical of A cosine theta. Notice here's theta, so here this angle becomes theta, and this side here is A cosine theta. Here we have this angle theta, which makes this angle theta, and again this line is A cosine theta. On the other hand, if you look at the opposite side, that is this side along the horizontal, we see that A prime has a component along A sine theta, and B prime has a component along minus A sine theta. If we add these two together, we can add the individual components, and we see that the components along the horizontal axis are wiped out, and along the vertical axis we have a contribution from A prime to be A cosine theta, and from B prime, double prime, also A cosine theta. When we add them together, we get 2A cosine theta. So this is A prime plus A double prime is going to give me a vector along this line. We have not made any contribution along the horizontal axis, so we only have a contribution along this axis. And if these are two lattice points and we connect them together, we get a connection. This new line by our lemma, A double prime plus A prime, is going to be equal to also to connect two lattice points. So now we'll combine all this to if A prime and A double prime are connecting two lattice points in a line like this, in a vertical line, that's got to be related to A by a whole number of integers. So this, or a whole number where m is an integer. So along the vertical component, we're going to get 2a cosine theta, which we saw from the previous slide, and that also is going to be equal to m times a. Now we know that a cannot be 0. It connects two distinct lattice points, so we can remove the a from the above equation, and we get 2 cosine theta equals m, which is really an extraordinary statement. We can divide by 2, and we see that cosine theta is equal to m over 2. Well, now we have a very, very interesting situation. Are there any restraints on what this equation is? Think of cosine. What's the maximum you can have of a cosine? Plus 1. What's the minimum is minus 1. So that means that the cosine has to be between, the cosine of theta has to be between plus 1 and minus 1. That means that m over 2, which is equal to the cosine of theta, must also be equal to m over 2. So here we can write that out, and we can substitute the m over 2 and multiply by 2. So that means m, the integer, has to range between minus 2 and plus 2. There aren't many integers between them, so let's write them all out. M could be 0, and in that case m over 2 is 0. That's equal to cosine theta, which means theta is equal to 90 degrees, and if theta is not equal to 90 degrees, we have a fourfold, because 90 into 360 gives me 4, or a fourfold. Let's examine some of the other examples. If m is equal to 1, m over 2 is a half, theta is going to be 60 degrees, and 60 into 360 gives me a sixfold. If m is equal to 2, m over 2 is going to be 1, theta is going to be equal to 0, or 360, or multiples of that, and we come up with 360 divided by theta, or 360, we get 1, so we have a one-fold, or the identity. We have m equal to minus 1. M over 2 is going to be minus a half. We've seen this before. The theta is going to be equal to 120, and we have a threefold. And finally, our last one is going to be minus 2 for m. M over 2 is minus 1. Theta is equal to 180, and n is equal to twofold. The enormous implications, the enormous results here are that we only have 5 possible cases. We can have the identity, twofold, threefold, fourfold, and sixfold if we are to have a periodic lattice, or a lattice which is a periodic object. We limit ourselves to these rotation axes, and that has a profound influence on crystallography and everything else in this course. It's also, again, it shows us that a 5-fold, a 7-fold, a 35-fold, a 999th fold, none of those symmetries are permissible in a lattice, in a three-dimensional, or two-dimensional, or one-dimensional, or n-dimensional periodic plane. So here's the summary. We are only allowed 1-fold, 2-fold, 3-fold, 4-fold, and 6-fold operations which are consistent with a lattice. And I want you to remember these and be able to chant it out. And now we come to the end of this section. That's all for now, folks. See you later. Bye.